So in the previous video, I told you that I would give you 5 different ways of improving the scalability of SMP, symmetric multiprocessors. But I only showed you 4 examples. Here we're going to look at the 5th way of improving SMPs, and it's to use a directory-based protocol instead of the Snoopy-based protocol. So we briefly discussed this before. There are 2 different options for implementing coherence: the Snoopy-based broadcast kind of protocol, and the directory-based that I here refer to as a point-to-point protocol. As you will see, there are very different techniques for used to implement coherence in these 2 schemes, but they also have lots of variable scalability that comes as a result. So here it is, the 5th option for building scalable SMPs, directory-based protocols. So this is a system where we connect the caches and the memories using a general interconnect. It doesn't have to be a broadcast interconnect. It could be any kind of network technology that can carry a point-to-point message between a cache and a memory and vice versa. This means that the implementation can be more scalable since we no longer have to rely on any kind of broadcast media. So we scale to more nodes, but as you will see, we also get an even higher latency here because more often we have to go across this general interconnect to the memory, and more specifically to the part of the memory called the directory. There's been numerous examples of commercial implementation using this technique. From here is the V9000 is probably the most famous one from HP. So now we're going to look at how to do this, implement this kind of point-to-point cache coherence directory-based protocols. So let's first remind ourselves what actions are taken in a Snoopy-based cache coherence protocol. And this is the example where we would like to, the middle node wants to store, make an update to data that is shared in several caches. So what you do here is that, of course, you broadcast the bus invalidate that will be snooped by all the other caches, and they will invalidate their copies eventually. As soon as you see your own invalidate on the bus, that is the signal to you that you may now change the value of that cache line. And then we had the other example where the node to the left wanted to read the newly changed data. It sends out a bus read to share request. The node in the middle detects that this is a read request for data it just changed. And the node to the left will see its own bus read to share on the bus and put it in that FIFO, waiting for the data to arrive. And here's the data, and now it can actually read that value. So that's how we implement the Snoopy-based cache coherence. In a directory-based protocol, we don't assume that we have any broadcast media. There is, as I said before, a general interconnect. Right here I actually show no interconnect at all. I just show that all caches can sort of speak to the memory, and the memory can send messages back to the caches. One difference here compared with the previous example is we have added some metadata to each cache line, and the metadata keeps track of which of these caches that has a copy of that specific cache line. So the metadata of the gray cache line would remember that there are shared copies in all these caches. Now, when the middle thread wants to make an update to the shared cache line, it cannot send a broadcast message to its fellow caches. Instead, it sends a point-to-point message to the memory. The memory says, I can see that lots of caches have shared copies, so I better send invalidation messages to them. Those caches will send acknowledge signals point-to-point to the cache in the middle, promising that they have now destroyed their data, and the middle cache will send an acknowledge back to the directory just to close the loop, telling the directory that this action has been done. So let's look at that video again. Sending the request, point-to-point, acknowledges point-to-point, and then it's a point-to-point message eventually sent back to the directory. Likewise, when you would like to, the node to the left wants to read a piece of data, And now once more we assume that that data has been modified, so it lives here in the middle cache, the modified value. So then the node to the left sends a point-to-point message to the directory. The directory will know that it's the middle cache that has a piece of data. It will also know that the middle piece of data is dirty, so the memory knows it cannot use its own data to reply to this request. So it sends a read demand down to tell the middle cache to forward the data to the left cache, and then the left cache finishes off by sending an acknowledge to back to the directory. So let's play that move again. If you would like to implement sequential consistency in a directory-based scheme, you have to be a little careful, because now we don't have this bus, Snoopy bus, upon which we can easily define which order all the transaction happens in the system. This is an interconnect where several transactions can be sent at the same time. Several transactions can miss each other, sort of in the air in this general interconnect here. So the way you implement sequential consistency, and we already saw that in the previous example, but I just would like to highlight that once more, is by sending the invalidate to the directory. Directory sends invalidates to all the caches that needs to be invalidated, and you have to stand here and wait until you receive all the acknowledges from all the caches. Because then and only then can you be sure that all those copies have been destroyed, and since there is no ordering bus media, you really have to collect all the acknowledges before you are allowed to change the value in the cache and send acknowledge back. So that write in the middle here has to collect all acts before the write is performed. Okay, so that's how directories work. Now let's just once more look at the properties of the Snoop that we really enjoyed before and put them in contrast to what's happening in the directory-based system. So how is sequentially consistency achieved in a directory-based coherence protocol? So as we saw in the previous example, the writer waits for acknowledges from all the other caches before it may modify the data. So do you remember how sequential consistency was achieved in the Snoop-based cache coherence protocol? So it's simply just the order of all the read to shares, read to writes, and invalidate that occurs on the snooping bus that defines the order. So in contrast between the directory-based protocol, where we had to collect all acknowledges from all the other caches before we could go on and write the data, in the Snoopy-based protocol, it was enough for us to just see our own invalidation transaction on the bus. And once it's been on the bus, we knew that our write had been ordered in the global order system, and that was okay for us to change the data. So what was the advantage of the Snoop? Well, the Snoop is a serialization point that helps to implement coherence, and even more so, it helps to implement stronger memory ordering models. It can provide a very fast upgrade to a cache line. So an upgrade is a cache line that's in state shared, so we have read permission, but we do want write permission to that cache line, and that's what's called an upgrade, and that is simply done by sending your own invalidation on the bus. It also has an advantage that cache to cache is faster, and as a side effect, so since synchronization typically are combinations of upgrades and cache to cache transfers, synchronization can also be implemented faster on the Snoop-based protocol. So that's why we use them, but the major reason for moving away from Snoopy-based to directory-based is that it's very expensive. Even if we use those first 4 tricks of improving the scalability of the Snoop implementation, it is still very expensive to do so, and there is an upper limit to how far you can push snooping. So moving forward to larger systems, moving forward to faster technologies, you will see more and more implementation using directory-based coherence.